Kalantari, who will speak about the globally convergent Newton method for polynomials.
Thank you very much, Professor Zalberg here. It's always a pleasure and great honor to lecture in your seminars. So, Newton's method, everyone is, of course, familiar with. The first thing, what comes before Newton's method is the fundamental theorem of algebra, that every complex polynomial of degree bigger than or equal to 1 has n roots. Degree n has n roots counted with multiplicity. I guess everybody knows complex numbers here is of this form. And complex variable z is x plus iy, modulus of a complex number, and polar form of a complex number in terms of its argument and c, its modulus. So an interpretation of the fundamental theorem of algebra is in terms of the modulus of the polynomial. And if you have a polynomial, its modulus is a function of x and y. It's not always so easy to write this function. For cubic, it's this. And if you graph it, it's going to look like that in MATLAB, for instance, or Mathematica, or whatever. So the surface, fundamental theorem tells us that it lies above the xy plane, and it touches down at these points. As many as its roots counted with multiplicity. Newton's method is for root finding, probably one of the most famous algorithms in mathematics. The formula is z minus p of z over p prime of z. That's the iteration function. And Newton's iteration is you pick a seed, z0 in the complex number, and you iterate. And you consider the sequence of points that are generated. This is called the orbit of the sequence, forward orbit. And this method is familiar to even some high school students. Basic properties of Newton's method is that it's related to theta is a fixed point of Newton's iteration function. If and only if theta is a root of p of z. This is not always true for iteration functions. In this case, there are no extraneous fixed points. And if the derivative of Newton's function at theta is less than 1, then when the seed is close enough, the iterations converge. In fact, if it's a simple root, it converges quadratically. So we really need, say, 5-6 iterations, no more, to come close to a root. So the rate of convergence is quadratic. Based on attractions, if you have a root theta, we consider all those seeds whose iterations under Newton's method would converge to a root. And this is an open set, A of theta. Basin of attraction of each root is open. There is a connected component containing theta itself. It's called the immediate basin of attraction. The orbit of any boundary point of A of theta cannot converge to any fixed point or any infinity. So there is chaos if you iterate along the boundary. Julius set is the boundary of any of these basin of attraction. Hence, it's a closed set. It's often a fractal set. A Fatu set is the complement of the Julius set. Hence, it's an open set, countable union of connected components, called Fatu components. Polynomiography, a term for visualization of the process of polynomial root finding via iteration functions. Here's the definition. Polynomiographs may or may not exhibit fractal features, but visualization of Newton's method generally has fractal features. I have noticed that mathematicians or otherwise refer to images that are sometimes not fractal. They call it fractal. I don't know why. Some people think that anytime you have an image based on iteration, it must be fractal. That's not true at all. Polynomiography not only is a useful tool for mathematicians, is what I believe, scientists, educators, and students, but it could attract artists and amateurs into working with polynomials.
And sometimes the same person, like in your case.
It's not yet a familiar term in case 16, but that's not the fault of polynomiography. I think that is maybe the way we do education. Just today I read an article in the New York Times that a professor came up with a remarkable formula, way of describing formula for quadratic, to make it easier for us. I don't know why we need to make things easier. Let's make it a little bit more difficult and introduce them to difficult concepts. Some Newton's method polynomiographs. The left image is the polynomiograph of z squared minus 1. The roots are sitting here and here. And the right image is a polynomiograph. If you put an alpha in front of this Newton step, you get, with the right alpha, you get this. I did this thing in South Korea to a group of middle schoolers. I showed them how they can generate the map of their country using Newton's method and the quadratic, and they were very excited to see that. Anyway, you see there is no fractal property here. So the basin of attractions are just the Voronoi region of the roots, and nothing converges on the boundary to infinity or to a finite number. Now the question, what is the polynomiography of Newton's method of z cubed minus 1? This question was investigated, the shape of these by Cayley, in fact, who is credited for being the first person who introduced, who suggested doing Newton's method over the complex numbers. This is what Cayley thought. And I guess the story is that he did it for quadratic, but for cubic he somehow couldn't do it, and of course he couldn't visualize it. So he never wrote a paper on the performance of z cubed minus 1, explaining it. Actual polynomiograph is this, which has this fractal patterns. So this became a well-known figure at some point. And I'm just giving you an example of the polynomiograph which is not cubic, which is not for cubic, which is not fractal. Here is another non-fractal polynomiograph based on a method called Newton ellipsoid polynomiography, which has appeared recently in the Journal of Mathematics and the Arts. So you can make art, or you can this combines two fantastic methods for optimization in Newton's method. What are the shortcomings of Newton's method? It's not defined at the critical points. If p prime is 0, it's not defined. It only guarantees local convergence. Even for cubics, the question whether the orbit of an arbitrary point converges to a root is undecidable under the theory of, Smale and these folks. So, and it may perform in a poor way in the sense that the next iterate, the modulus of the polynomial at the next iterate could be larger than it. So these are pathologies. It could behave chaotically. For instance, in this example, polynomial taken by Smale, we have 3 roots, 3 colors, plus these white areas. These white areas are bad. If you pick a point seed within those white areas, it doesn't converge to any of the roots. So Newton's method could be poor. Smale's one-point theory is one of the nicest.
So in the white regions, it just stays in the white region, never goes out?
Sorry?
In the reaches
The
at one
polynomial, it just cycles. It just, for instance, a neighborhood of 0 gets mapped into a neighborhood of 1, and a neighborhood of 1, so it cycles, and yes. And you see it has a positive measure here, so it would be bad, of course. Smale's one-point theory is one of the nicest results on Newton's method. It says if you have a seed Z0 and you compute this number, where higher derivatives must be computed of the polynomial, all the derivatives actually. And you look at this, and if this number is less than or equal to this quantity, then we are within the quadratic region of convergence, in the sense that if you start iterating, in j iterations, you get within 0.52 to the j. So it's very quadratically converging to some root. It's normally not written like this, Smale's condition, but I'm writing it because it's more convenient to what I'm going to present. Okay. Computing all roots via Newton's method. I mean, I was teaching numerical analysis last semester, and I did some of the stuff there, because usually numerical analysis books don't even get into the complex domain. And maybe the impression that people have of root finding is that, well, it's all, it's an old-fashioned problem, but in fact it's not. For instance, computing all roots of polynomials, there is this paper by these authors in 2001, where they show that there is a set of these many points using sophisticated, really, mathematics from dynamical systems, where if you start Newton's method from these, it will converge to all the roots of the polynomial. And of course, not necessarily quadratic rate from the beginning. It may be slow at the beginning. And in fact, in this paper, they consider this idea for finding roots of polynomials of degree 1 million. And even in the later work, these are on archive, billion degree. And they report that these are theoretically also competitive or even better than some of the classical methods for root finding, which are based on divide and conquer kind of algorithms. Now, robust Newton's method is the basis of this talk. I'm going to describe what I call robust Newton's method. It's a stronger version of Newton's method, where given any seeds, yes?
Your previous point, could you elaborate, like, for example, how do the iterates look like? Like, it goes to one root and then somehow can still move on and then traverse it. Like, how does it...
Oh, you mean those, I guess they just go to one root.
You said if you find, starting from one of those seeds, they can find all
They
of them,
can.
right? So how does that work?
You're talking about their method?
Yeah.
Well, I'm not explaining the details, but imagine there is a set of about n logs squared n, so that if you iterate from those, for each of them you converge to a root. Yes, you will have more than one conversion to the same root. But it doesn't go back and forth. It just converges to it.
So what is the shape of this set?
Sorry?
How does this set look like?
Sorry, my hearing is very bad, so I have to come.
How does the set look like?
How does?
The set look like?
Oh, the set is, it's a complicated set. You should really see their paper. It's a very, sophisticated paper. It's not easy to describe. Now, in robust Newton's method, it has a property that you take any seed, whatever, and you iterate, it will either converge to a root or to a root of the derivative, a critical point. That's not bad. So it's okay. First of all, descent direction of Newton's of modulus of polynomial. Again, let's take the modulus of a polynomial. Let's square it for simplicity. So it's p of z times the conjugate of p of z. This is a polynomial in x and y, two variables x and y. We say at a given z0, we say u is a direction of descent if there is some alpha star so that this inequality is satisfied. In other words, it just goes down for a certain length. Now, the cone of descent at z0 is a set of all such directions. The question is, what do they look like? This is a geometric modulus principle, I called it, in 2011, it's in monthly. It says, take any non-constant polynomial, take any point z0, which is not a zero, then every direction at z0 is a descent direction for p of z. That's obvious, right? If it's a root, the polynomial is not a constant. I mean, it's not a non-constant. It has to be increasing. And if p of z0 is not 0, then the cone of ascent and descent directions at z0 partition the unit disk centered at z0 into alternating ascent and descent sectors of equal angle, pi over k, where k is the smallest index with pk of z 0 not equal to 0. In picture, okay, specifically if k is bigger than or equal to 1, it is the smallest index such that that is not 0. You form this number, write it in polar form, and e to the I theta is an ascent direction if it lies between these two. Never mind the details, I'll show you a picture. In picture, this is what the polynomial looks like. Take any polynomial, non-constant point, take any point. If it's a 0, every ascendant is direct. If it's a typical point, 50% ascent, 50% descent. There is some neighborhood where it has this property. Okay, ascent just means it's going up. I'm not saying how much. It may not necessarily be the same amount at every point. If the first derivative is 0, but the second derivative is not a 0, it splits like this. And this is when the first and second are 0. So it's very nice. I was surprised why this thing is not done. And using this property, it was 2011. At that time, I just wanted to get a pick in the monthly, so I didn't try to expand on it. For instance, if you look at z cubed minus 1, at the origin, which is a critical point, the first and second derivatives are 0, so it splits like this. Okay. And what is the application of it? You can prove the fundamental theorem of algebra very easily. You take any point, if it's not a 0, there is descent. You just need to show that you can take a big circle outside of which it goes to, it's not, everything, you limit it to a compact set, and then you show the minimum is attained. If the minimum is not 0, you get a descent direct contradiction. Also, you can prove Gauss-Lucas theorem, which says critical points must lie in the convex arc of the roots, and more. Now, what is a robust Newton method? So I told you it has this property that for any z0 converges to a root or converges to a critical point. So it's more elaborate to define it. Take any z where it's not a 0. Let k be the minimum j such that the j derivative is not 0 and j bigger than or equal to 1. Define a of z to be maximum of this normalized derivatives, and define uk to be this number. Define ck, and so on. So you have to define all these parameters, and it's not important to know the details. And then you also have to pick an angle. Okay. Then remember the descent directions, or like say the white areas are descent, right? So we have a lot of choice if we have a critical point of choosing descent. You can choose Newton's direction if it's not, if the derivative is not zero. So robust Newton is, I put this hat, it looks like, it's more elaborate than Newton's method. You have to define these parameters. Z gets, this is the robust Newton iteration. When k is 1, which is most of the time, in other words, you want to have at most n minus 1 critical points, the iteration, you see, it's almost like Newton's method, but it has this modification. So I make sure that when you take Newton's method, for instance, I mean, if you take the typical Newton's method iterate, who knows, it could go up. And you know that if it's not zero, it should go down. But then what step do you take? So here I'm giving a step, a specific step to take the Newton direction. And we can define the orbit under this. I should maybe mention that, you see, this is not a rational iteration function because it has this modulus thing. But so what? If I'm trying to find the root of a polynomial, I'm trying to find the root of a polynomial. If I'm trying to do dynamical system, that's a different thing. So here we can define an orbit at a specific point. And what is the complexity of each iteration? We know that in ordinary Newton's method, we can use Horner's method to do O of n. In this case, we need to compute normalized derivatives, but you can do that in n log n. N squared log n, for instance, is easy to see. So they can be done in O of n log n as opposed to n squared. And so now the nice thing is that it's defined everywhere. At a non-critical point, the step size is a positive scalar multiple of actual Newton's method. And in fact, it's within 1/9 of Newton's direction. 9th of this is called Newton's direction. This modification of Newton's method, together with the ability to define the iterates at non-critical points, will guarantee that the modulus necessarily decreases by a computable estimate at that iteration. So, I call this Modulus Reduction Theorem. So, it simply says that if you iterate, then the modulus at the new point, Z1, minus the modulus at the starting point, I mean the given Z0, goes down by a certain amount. Okay? And if k is equal to 1, it goes down by this much. So we can estimate, exactly how much it's going down. Yes?
So all these statements only hold if you are looking at a polynomial. What if I were to look at general Newton iteration on a non-polynomial function?
I am only caring about polynomials because they are nice. And
Sure.
I think once you do polynomial, for instance, GMP, I think you can do it for more general analytic functions. I believe. But it's a very good question. I think actually it may not work for any analytic function, for instance, this, because you need to estimate, these derivatives. It's a very good question. I think there are really many questions regarding this robust Newton method. So this RNM assures reduction of the modulus moving from Z0 to Z1, which is what Newton's method doesn't do. We can bound this A of Z, this number that finds modulus, because if we know the roots, we can find bound on the roots, and then we can say, okay, within this, bounds, this is how big this can be. So we don't even need to do n log in every iteration. And so the amount of reduction is basically proportional to this at a typical point. Okay. So the modulus reduction is just replace zk z0 with this n hat of z0 and repeat the process. In contrast with standard Newton's method, the additional work is a computation of that. That can be boundless. The basin of attraction of a root theta under iterations of R and M, let's call it A hat of theta, and is a set of all O hat or orbits under robust Newtonian iterations. Now, we can define this algorithm basically. Given a polynomial of degree bigger than or equal to 2, and given epsilon, iterate while these two are bigger than epsilon, do this iteration, robust Newton iteration. And here I want to show you a polynomiograph of how they differ. This is under Newton's method. This was the z cube and so on. You see this bad region. This one. Now, this is what you get for robust Newton. I think this would have made Cayley happy because this looks like the coronal regions, the basin of attractions, are just the coronal regions. So you see it smooths out. Those white areas disappear. Okay. Convergence and complexity, given epsilon as z0, suppose S0 is a set of all defined according to that. And let's, first thing is that the orbit of Z0 is in S0. Obvious because the moduli are going down. Again, now let A0 be the maximum of these when Z0 is in this. Then, and delta epsilon be equal to this, then the least number of iterations that will satisfy either less than or equal to 0, or this less than epsilon, and this or this less than will satisfies this property. 1 over epsilon squared. You might say that's maybe this can be improved, but I'll say more about that. Also, look at this now. If you pick, suppose it has no double roots. Okay, so let's consider the critical points. Let's look at the modulus of the polynomials at these. And let's pick the minimum of these. If you have any point that has modulus less than m, it's going to converge to some root. So, okay. And this says, for any root, the basin of attraction of A of theta contains an open disk, like ordinary Newton method. Okay? And if you have a critical point, what happens? You remember here, if you have a critical point, for instance, if say these are descent directions. So if you pick any point here, the next iteration is going to go below this. So you're never going to get close to this critical point. Maybe if you are here, which is ascending, maybe the iteration one would think that it comes here. It's but in fact, if you're lucky, it comes here, the next iteration, which means again it will escape, the critical point. So this is a nice property. The critical points cause trouble, but maybe not too much trouble. So if P of z is less than or equal to m, then this converges. And as long as this is bigger than or equal to epsilon, each iteration decreases by at most that much. Now the problem could happen that this is bigger than epsilon, but this is less than epsilon. This is the problem. Okay. I don't want to get into details of that, but you may say one of the shortcomings of this geometric modulus principle is that, or this reason is that it only defines it at critical points. What if a point is a near critical point? Well, the remedy is to treat it like a critical point. So rather than defining Newton's, go to its next. So with some detail, you can define a modification of Newton's method, which one can show. I don't want to spend too much time on that, but you can define a scheme which I call modified robust Newton method, which avoids the critical points. However, in this case, I cannot say exactly how many, in terms of epsilon, how many iterations. That's open. Avoid coming to a critical point. And so we can prove that given any seed, the orbit under Z of modified RNN converges to a root of cubes. Given epsilon, there is an iterate ZT such that this is the same. What is it in terms of epsilon? I don't know that. Now, if you look at Z squared minus 1 under robust Newton method, see, this is the critical point. Okay, we're looking at the complex plane. So everything here converges to 1. Everything here converges to minus 1. What happens to the points on the y-axis? Those will converge to the critical point. Okay? And if you're at this critical point, the next iterate would be this one. This doesn't mean that, I mean, I could have made it so that it would converge to that, because I have two sectors of descent, right? So, and if you do this trick, where a near critical point, you do the modified Newton's method, then instead of moving down here, it's going to jump to here. From that point on, it goes to, converges to minus 1. So for quadratics, one can prove the quadratic without Gaussian generality can be taken to be Z squared minus 1. Under RNN, the basin of attraction of minus 1 and 1 are the Voronoi regions. Also, basin of attraction of the origin is the imaginary axis. Under modified RNN, basin of attraction of minus 1 is the Voronoi region and its boundary. And the basin of attraction. So we essentially force the boundary to converge to one of the roots. Okay. And now a cubic polynomial. How do we solve a cubic equation? We can, of course, use the formulas, but I don't remember those formulas. I don't know if anybody remembers in this room what formulas for solving a cubic polynomial. But here I give an algorithm, a new algorithm for solving a cubic. How does it work? Say a general cubic like that. Let C be the critical point which has a smaller modulus. That's a 2. So you solve a quadratic equation, you evaluate the moduli at these points, take the smaller one, maybe they're equal, doesn't matter, then start the robust Newton method. It will definitely converge to.
Yeah. But it's not an explicit answer.
Sorry?
It's an approximation.
Well, you're right. But so is if you have cube root of something, you have to approximate, right? We can, even quadratic formula. I mean, to this article which I mentioned in New York Times, formulas about quadratic equation. It's unfortunate that in high schools they don't speak about Newton's method. If you have the quadratic formula, x squared minus 2 equal to 0, so you write the square root of 2, but what is the square root of 2? So you have to iterate. So here is, and of course once you have one root, you then factor out and you complete the other roots. Now, if you have this polynomial, Smale's example, these are the critical points, right? And a neighborhood of 0, or 0 is mapped to 1 and 1 is mapped to 0. So suppose that we are here and we want to reduce the modulus of a polynomial. How can I reduce it here? Literally, I have to go into the board, into the complex direction to be able to do that. So as a general philosophy, I want to say this. Okay. I mean, that's why I think if you want teachers numerical analysis and doesn't mention complex polynomials, it's you are not really appreciating polynomials. So I mentioned this for a cubic. To get a root, we have to move into the complex plane. While Newton's method is undefined, taking a step, reducing the modulus with R and M, we can take a step. The Modulus Reduction Theorem assures that the orbit will converge. Now, this Modulus Reduction Theorem uses two auxiliary lemmas. I mean, I must say, maybe two things really are used here, or I should say three things. One is the Geometric Modulus Principle was the motivation for developing this. Although this was my 2011, I hadn't thought about this application before. But it also uses these two auxiliary lemmas, which are really like, calculus lemmas. The next one is, says you have this function. And essentially, I want to get a capability to reduce the modulus. I use these two lemmas. So let's not worry about that. Complexity of each iteration, I already mentioned, is n log n. But maybe we can do the normalized derivatives, can compute it every so often. For instance, every O of log n iterations. Now, you might say, what if Newton's method does better than robust? What? At each point, take robust Newton iterate and Newton iterate, and choose the one that has a better modulus. That's one. Robust Newton method and Smale's 1.3. Here, Smale's condition gives you quadratic rate of convergence. So, and notice that the robust Newton method works with the same thing here. If this is small enough, Smale theory implies you have quadratic convergence. And if this is not small, then the robust Newton method is going to decrease it. So, by a certain amount. So it complements Smale's condition. Computing all roots of a polynomial. How would we compute? We know that RNM can be combined with deflation in order to compute all roots. Suppose we have computed an approximation to a root. We can factor it out. We get this factorization, and by continuity, roots of Q of Z approximate roots of P of Z. So now I try to apply robust Newton iterate to Q of Z. Once I've iterated enough, then that root is going to get far away from the first approximation. Now I can go back to P of Z and apply robust Newton method again. And you can do this with all roots, in fact. It is my final remarks. By considering minimization of the modulus of a polynomial together with utilization of the Geometric Modulus Principle, we have developed a stronger version of the classical Newton's method called the robust Newton method, where the orbit of an arbitrary seed converges either to a root or a critical point. Each iteration monotonically decreases the modulus. We can also describe a modified version that converges only to roots. The results really are accessible to educators, students, and useful for researchers, generating non-fractal polynomiographs, computing all roots, and comparing the results with other techniques. It gives rise to research problems also. When I gave this last semester to my numerical analysis student, I also gave them a project to write codes for this. So here are two links where I would thank them specifically in the final form of the article. But one of them generates the polynomiograph. The other one actually gives an implementation. You input your polynomial and it computes all its roots. Of course, the small degree polynomial. And I like to end with a conjecture. There are many things that I don't still have a good feeling for. I like to give this conjecture that the R and M based on our attractions for Z to the n minus 1 is its Voronoi region of the roots. And this is for x z to the 4 minus 1. Okay. So,
So do you know it's for small n? Do you know it's for n equals 4?
I mean, I have only done it for z squared minus 1 and equal to 2. But the figures in z cubed and z4 seem to suggest that this is true. In other words, you want to show that when you are near a critical point, because the origin is a critical point for these, you can escape it. You know, it escapes for itself without going to this modified robust Newton. And so this is a very simple example of a polynomial. We know that this is not always true. The example of Smale, z cubed minus 3z plus 2, for that we had to remember we had to curve in there. But, and so, as I mentioned, there is this, say from a research point of view, there are these results based on dynamical systems for computing all roots of a polynomial. And here we can converge to anything, you know. So maybe, can we improve the complexity that in 1 over epsilon squared converges to a root, or essentially a critical point? Can we improve that? Is it really the case that it's 1 over epsilon squared if you use, say, Smale's condition? So there are open questions, and also, as the gentleman suggested, maybe it's generalization to more functions, you know, more to analytic functions, for instance. So I guess.
Questions? I have a practical question. So if you go to Maple Mathematica and you solve the polynomial, can your algorithm compete without speed?
What do they do though? Do they compute all the roots?
Yeah.
I think possible.
Yeah.
Because if I'm finding the roots, now generation of these images,
yeah,
according to the students implement, I haven't implemented these myself,
yeah,
is slow.
yeah.
But that's because they're trying to do this for every point, and they're not necessarily doing it efficiently. You know, if I'm finding a root, I don't need to generate a polynomial. So I believe that, I mean, I think, I don't know what algorithm they're using, but for instance, Pan's approach uses White's method, where they take a square, all the roots, and then they divide it into sub-squares. For each one, they do this test, and they keep subdividing into this. The other approach, you know, as I mentioned, is scale, 1 million roots of a polynomial. And we say, how do you get such polynomials? They get it from you know, related to Mandelbrot's iterations that comes from there. So maybe their polynomials are very special.
Oh, so it's not an arbitrary polynomial?
Yes, they don't take it. They haven't taken arbitrary polynomial. But they say this is complete. I mean, this polynomial root finding is a never-ending thing. You know, it's, I don't think it will be clear really what. But maybe we can, I mean, it's definitely this, I think a good, maybe PhD research would be to try to compute all roots of a polynomial using robust Newton method and analyzing its complexity and comparing it with others.
Another question, can you explain to quaternions, for example?
Sorry?
The quaternions?
Very, very nice question. I haven't really thought about it. Yes, that's an excellent question.
Oh, yeah, I had a question. In the diagrams that you had for the cones of ascent and descent,
yes,
it made it seem like the cones had a uniform radius. Is that true? Or are they actually like jagged or something?
Yeah, I mean, in reality, you know, maybe it's like
Something
that.
like that. Okay.
Yes, but even in such a thing, I can choose.
So you can choose a uniform.
Yes,
as a
you
small
can choose a bar.
Okay.
You can choose a bar. It's a, you know, very, I mean, as I said earlier, I think this is such a nice property. Where such a, you know, this is really what distinguishes the complex polynomial from, non-complex polynomial. The polynomial is an excellent approach. That the splitting is so even, 50% always. So at random, you pick a direction, you have 50% chance of it being the descent direction. But how big it is, I really don't know that, like for instance, or for even z squared minus 1 or z to the n minus 1 at the origin, it would be nice to see what the actual shapes are.
Well, let's take a
Thank you very much.